All right, hello, welcome back. So as promised, now we're gonna get into more quantitative descriptions of thermal and bond energy, which will allow us to answer some questions about these thermal interactions, more specific questions. For example, we can ask, given some amount of heat that we're adding to the substance. So you know that you put a glass of water in the microwave for 5 minutes. Given the power of the microwave, you can more or less ballpark how much heat you have added there. And from that, how can you figure out how much did the temperature of the water changed after, let's say 1 minute? Or you could say, ask, given some amount of heat added to a substance, how much did that substance change its phase? So it could either be going through a temperature transition or a phase transition. These are the two things that we've been focusing on. So the answer is both of these things depend on the amount that you have and the type of substance. So, for example, it takes much more energy to heat a bucket of water. You know this from everyday experience comparing to a cup of water. With this too, a huge piece of ice will take more energy to melt compared to a small piece of ice. Or we also saw that from the three-phase diagram, we saw like a short line for melting and a very long line for vaporizing. So we kind of intuitively discussed this, that it takes more energy to break those bonds that take the substance from liquid to gas versus the bonds that are broken to take a substance from solid to liquid. So it depends also on the type of phase you're in. And we'll also see that it depends on the type of substance. So not the same amount of energy is required to heat water as required to heat another type of liquid, and same for solids and things like that. Okay, so this is how we write these concepts mathematically. So thermal energy, remember, was the energy that described the energy that was changing when temperature was changing. So the change in thermal energy has to be proportional to the change in temperature. If delta T is positive, temperature is increasing, so is change in thermal energy. But it also depends on proportional to mass. So if you double the amount of stuff that's changing temperature, going to double its thermal energy. So you will need to add double amount of energy to heat 1 glass of water compared to 2 glasses of water. Now this C, we will go into that detail shortly. This is known as specific heat, and that's directly related to the type of substance we're dealing with. Now when bond energy is changing, that has to do also with the amount of stuff you have. So that's the mass. And then there's this constant, which is known as we'll go into more details about this, but it's either the heat, it's enthalpy. So it has to do with the changes of bond energy when you're going through a specific phase transition. So there's going to be heat of vaporization and heat of melting are the two quantities, and it will also depend on the type of substance you have. Now the plus or minus sign here, so the way that, what does that mean? So the way this equation is set up is we put absolute values here. So we're just always assuming that this M represents just some amount of mass that has gone through that phase transition. So we're not really concerned with, are we getting more liquid or in a melting situation, or are we getting more ice in a freezing situation? It's just all that you put in for this M is that, let's say 100 grams, normally you'd have to convert it to kilograms of ice melted, and you put that number in. And this is a constant too. Now the plus or minus, that will have to, that will tell you whether the bond energy is increasing or decreasing. So you have to put that in depending on which process you're describing. If the substance is vaporizing, we've talked about that. That means bond energy is increasing. This will take a plus sign. If the substance is freezing, for example, bonds are being formed, bond energy goes down. So you put in that minus sign. So you have to determine that sign based on which direction the phase is changing. Now for thermal energy, the sign naturally comes from delta T. So if your delta T is positive, if you start at 0, this delta T always means final minus initial. So if you start at 0, you end up at 20 degrees Celsius. 20 minus 0 gives you a positive number, so your delta E thermal is positive. If on the other hand, your object is cooling down, let's say from 10 degrees to 5 degrees, 5 minus 10 gives you minus 5, so you get a negative change in thermal energy. So here the sign comes naturally, here you have to choose the sign. So it's kind of a subtle thing that you need to keep track of when you're working these equations. Okay, so let's go into more details about the meaning of this little c. Okay, so heat capacity is defined. So we'll start with heat capacity, which is capital C. In the previous equation, it was lowercase c. So I know it's a bit subtle, but there's a difference. So heat capacity is a measure of the amount of energy required to increase the temperature of some substance by a certain amount. So this equation tells us if, let's say we add some amount of energy, by how much would that temperature change of that substance? That's what gives you the heat capacity. So something that has high heat capacity, you will need to add more energy to have the same change in temperature. So for example, you have two substances, you add 10 joules to both substances. If one substance changed only by 1 degree Celsius, but the other one by 5 degrees Celsius, the one that had a smaller change, delta T was smaller, has a higher heat capacity. So you could kind of think about heat capacity as the resistance to temperature change, or another way of putting it is how difficult is it to change the temperature of a certain substance. If you need to add a lot of energy to just have a small change, that's kind of difficult in the sense that you need to keep on adding energy. So that's high heat capacity. So it's kind of the capacity of a substance to keep its original temperature. If it's high, it means it has high heat capacity. If it's low, it changes its temperature pretty easily. Okay. Now, heat capacity is what is known as an extensive property, because extensive just means it depends on the amount you have. So if we have 2 kilograms of water, it will have twice the heat capacity of 1 kilogram water. So in other words, to change 1 kilogram of water by 1 degree Celsius requires a certain amount of energy. But if you want to change 2 kilograms of water by that same amount of 1 degree Celsius, you would need to double the Q. So double the Q means also double the heat capacity. But that's not often a very useful quantity. You want to have a quantity that doesn't depend on how much substance you have. It just depends on the actual substance, water, mercury, gold, iron. You want to have a number that will tell you indirectly how the temperature will change given some amount of energy that doesn't depend on how much iron you have right now. So this is known as an intensive property, which does not depend on how much you have, and that's given by lowercase c. So I know they look very similar, especially because lowercase c and uppercase c are written the same way, but they're different. So watch out for this when you're working with this stuff. They have different meanings. As we will get into more details with this, these will also get subscripts because it will matter whether we're doing things at constant pressure, constant volume. But for now, you'll mostly be working with uppercase C, lowercase c, but we will mostly use lowercase c because it's a more useful quantity. It will tell us the property of your material per unit mass. So we won't need to know how much we have. Okay, so here are some kind of implications of heat capacity or specific heat. So water, for example, has very high specific heat. What does that mean? That means, again, if we go back, you need to add a lot of energy to water to change its temperature. Now, land doesn't have as high of specific heat. So when the two are interacting or in thermal contact, water and land, typically the temperature that the land will get, because the water has high specific heat, so it's again resistant to changing a temperature, then the land which is close to the locations where there's water tends to be pretty constant in temperature, because it's really the temperature of the water that, when the two things are coming to thermal equilibrium, that's going to be dominant. Kind of another indication of that you see on our planet is that if you look at Canada and Europe, they're pretty much on the same latitude, which means that they get pretty much the same amount of sunshine throughout the day or throughout the year. But we know that Canada is much colder than most places in Europe. So why is that? Well, Europe gets this Gulf Stream that brings warm water from the southern hemisphere. And because the water there is warmer, that affects the temperature of the land. It also explains that places that are more inland, far away from water, have typically have much greater variation in temperature than places, coastal California. It's pretty much similar temperature all year round, and even, going a little bit inland like Davis. I mean, there are other factors involved. But already we see much bigger fluctuations in temperature between winter and summer compared to the Bay Area and San Francisco, for example. So that's kind of one implication of high specific heat. Okay, so how do we distinguish heat capacity and specific heat mathematically? So remember, again, specific heat is something that's intensive, so it does not depend on the amount. So it's basically heat capacity per unit mass. Or if we're talking in terms of moles, which sometimes we will, it's per unit mole. So basically we can rewrite C, and remember C has units of joules per Kelvin because it's Q over T, delta T. And then if we divide it by mass, per unit mass, we get the specific heat. So capital C heat capacity equals to mass times the specific heat. And this M, little m, just means it's per unit mass. So it has to go with this M. So this M has units, let's say, of kilograms. Where here, if we're doing per moles, that we want to multiply that by the number of moles, because then this C is per unit mole. So depending on which one you're using. If you're using CM, you have to multiply by moles. If you're using CM, have to multiply by mass. Okay, so here are some examples of numbers. So, why do we choose, for example, to put a hot drink like tea or coffee into porcelain container or glass, a cup versus a glass? Well, porcelain has a larger specific heat. So this is given in specific heat units because it's kilojoules, units of energy per kilogram, so per unit mass per Kelvin. So it has a higher heat capacity than glass. I remember higher heat capacity means, or specific heat means, it means it is more likely to retain its temperature. So when the hot liquid is interacting with a cup, because of that high heat capacity, the cup is not going to change its temperature significantly. So when you hold it, it's not going to get as hot You know better than to put a hot drink inside a glass container. That glass container will get rather hot. Let's look at how a thermometer is built. So the thermometer normally has like an outside plastic casing that has high specific heat, and the silver material which is inside that actually gives you the reading has a significantly lower specific heat. So why is that? Because we want the silver to change its temperature closer to that body temperature. So when you have low specific heat, then when two things are interacting, the thing with the lower specific heat will most likely reach the temperature of the other object, in this case, the body. So it's more influenced by that temperature difference. So the lower specific heat helps give you a more accurate temperature of the actual body, but then you don't want the actual plastic outside to get as warm as the body. So that covering has a higher specific heat. All right, so then also when we kind of go, let's go back for a second, way back. One more thing that I forgot to mention when I was introducing these equations is that for now we will just say that Q equals to the change in E thermal, and that Q, the heat, is equal to the change in bond energy. Remember, there's also the work possibility, but for now we're just making the direct connection between heat and change in thermal energy. Of course, when we have a change in temperature, then there's no bond energy changing. So all the heat is going into thermal energy, and here all the heat is going to bond energy. We will modify this definition a bit later in the course when we go into thermodynamics, where we will include the treatment of work happening as well. But for now, we're just focusing on heat. So it's okay to say Q equals to change in E thermal, and then we can use that definition of heat capacity, which depends directly not in change in thermal energy, but the heat that's being transferred. So then when we go here, we can rewrite that Q is equals to, instead of the capital C, now we're using the mass times the specific heat times delta T, and that will equal to the change in E thermal. Okay, so now let's look at more details at the definition of bond energy. So again, I said it's known as enthalpy, but just to make it more specific to what we're talking about, when we're talking about phase transitions, we'll call it either the heat of melting, this delta H, or the heat of vaporization. So when we're dealing with melting, you would normally want to put like a subscript melt, and when you're dealing with, and it's the same whether you're going in one direction of the three-phase diagram versus in the opposite direction. So whether you're melting or freezing, we're going to have that same constant, and that constant itself is a positive value. And remember, you have to choose the sign depending on which direction. If you're melting, that's a plus sign, heat is being added. If you're freezing, that's a minus sign, heat is being removed. And then vaporization or condensing, again, regardless of which direction you go, we normally put this vape subscript here just to distinguish the two. And then typically, again, as you saw for water, the line for that transition, vaporizing transition, is much longer, so more energy is required than to melt. So the change in heat of vaporization is typically much larger than the heat of melting. Again, due to the fact that it's required, more energy is required to break those bonds to go from liquid to gas versus break the bonds that make solid into a solid versus a liquid. And this has units. So the heat of melting and vaporization has units now of energy per unit. It's also intensive. It's per unit mass. So it's energy per unit mass or mole, depending on which units we're dealing with. And then you could see that when we multiply it by mass, the amount of substance that went through a transition, then you get back the energy of units of energy joules, which is the units of energy. Again, also this M is not necessarily the amount that you have. So for example, I told you that you start with 5 kilograms of ice and 1 kilogram melts. How much energy did you have to put in? So you don't put the 5 kilograms, you only are concerned about how much energy did it take to melt that 1 kilogram. So you put 1 here. So it's really the amount, not the amount you have, but the amount that went through that phase transition. Okay, so just to kind of summarize, so here, this familiar by now graph of temperature versus energy as your substance is going through all these phase transitions. And if we need to calculate the energies required for each of these processes, what do we use? So the first step is the thermal energy because temperature is changing. Notice the subscript here. That S here means the specific heat of solid. So what turns out to be true is that the specific heat of solid liquids tend to be kind of similar, but there still could be a difference. And even more different is the specific heat of gas. And we will explain why that is later on in 7a. At this point, you don't need to concern yourself why that is, but if you kind of look carefully, you see here that this line seems to have a bigger slope than this line. What does that tell us? It tells us that you don't need to add as much energy to have a given temperature change. So what that tells us is that the specific heat of a gas will be lower than of a solid. But you have to be careful at this stage. All you have to worry about is when you're figuring out some calculation, and let's say you're trying to figure out how much energy it takes to warm up a solid a certain amount of degrees, what you will be doing is you will be looking up these constants in a table. So if we're looking at ice, you have to make sure you use a specific heat of ice. If you're looking at water vapor here, you have to make sure you're using the specific heat of water vapor. Okay, so for this process, we will be using bond energy. This is the M, the amount of mass that's melting. Here, I'm just putting the positive sign in front because we're assuming we're going in that direction. Now, again, this describes a change in thermal energy, but now you see the subscript says a specific heat for liquid. Here, again, bond energy, but now we're using heat of vaporization versus heat of melting. And then finally, thermal energy, again, where we're using the specific heat for gas. Okay, so just to kind of go back to that table, to summarize, so we've been focusing on thermal energy and bond energy. We know that the indicator of thermal energy is temperature, but now we also know the relationship between the indicator and the actual energy. The same thing with bond energy. We know that, how do we know bond energy is changing? When your substance is either going through a phase transition or there's a chemical reaction happening. And you will apply this equation in discussion lab, both to phase transitions and chemical reactions. And we use this equation to figure that out. Okay, let me now ask you a couple of questions to kind of bring some of these ideas together. So imagine that you put red hot iron, which has 1 kilogram of mass, into 1 kilogram of cool water. So the water is colder than the iron, in an insulated container, so closed system. No phase change occurs here. So the only possibility is thermal energy changes or temperature changes. Also, we know that the water has a higher specific heat than iron. So given this information, which statement is true here? Iron has a bigger change in thermal energy. Water has a bigger change in thermal energy. They have the same magnitude in the change of thermal energy, or still not enough information. So think about this. Go back, think about energy conservation, go back to thermal energy definition, and pause the video and then check your answer. So The answer is that they have the same magnitude of thermal energy. So why is that? Well, we have two substances. They consist of they make a closed system because they're not interacting with the environment. So if it's a closed system, we know that the total change of energy of the two substances has to equal to 0. We only have a thermal energy change in iron because there's no phase transition, a thermal change in water. So in order for these two to add up to 0, they have to be equal and opposite. So because this question had nothing to do with specific heat, it just asked you directly about thermal energy. To answer this, we just have to think in terms of conservation of energy. And because, again, only two energies are involved, they have to be equal and opposite. This word magnitude just means the actual absolute value. Yes, one is positive. The water will be positive because it's colder. The iron will be negative, but they have to have the same value. So if this is 10 joules, this is minus 10 joules. So the magnitude is the same. Magnitude just, again, means absolute value, ignoring the minus sign. Okay, same exact condition. So same statement here. We have hot iron, cold water, no phase transition. Water has a higher specific heat. But now I'm asking you about temperature. So the increase in the water temperature is equal to the decrease in the iron's temperature. Water has a higher magnitude of temperature change. Iron has a higher magnitude of temperature change. Not enough information is given. So now think about what that means. Okay, so now I'm asking you directly about temperature. Actually, well, choice A sort of didn't make sense because it said that increase in the water temperature. Oh yeah, no, it's true. So the water is the one that's increasing in temperature, and the iron is decreasing. So you might have thought, given the answer in the previous question, like they have the same change in thermal energy, they must have the same change in temperature. So you might have been tempted to answer A, but you have to be careful because the change of temperature is not directly related to thermal energy. It also depends on the specific heat. So if we take our energy conservation equation to the next step, where we now describe our change in thermal energy in terms of the mass and specific heats. Remember here, the masses are equal. I did that on purpose because when you have the equal masses, you don't need to worry about the effect of mass. The only concern is the effect of the specific heat. And now because the water has the larger specific heat, remember this quantity, C times delta T, has to equal to C times delta T for iron, because those have to be equal and opposite. So if this quantity is bigger, then delta T has to be smaller for water. So for iron, the change in temperature has to be greater. And again, we're talking about magnitude, so we don't need to worry about here whether that delta T is positive or negative. It's just how much did it change relative to each other. So the iron has a greater change than the water. The iron will get closer to the water's temperature versus the other way around. So for example, if you have your hot iron at 50 degrees Celsius and cool water at 10 degrees Celsius, you might think, have the same amount, they should meet in the middle. Like let's say at, right in the middle between 10 and 50, which is at 30. But that would only be true if they had the same specific heats. Because water has a higher specific heat, it's more resistant to that temperature change. So it will have a smaller temperature change, and iron will be the one with a bigger change in temperature. So here, it's kind of fun to now, we've been sort of talking about it abstractly in terms of equations and specific heats and stuff. Let's actually kind of take a step back and try to use our ideas of energy conservation to understand some everyday physical phenomena we observe. So, one common thing, especially for those of you who wear glasses, that I'm sure you've noticed, is that, on a cold day, especially if you walk into a warm building, what happens? Your glasses get all fogged up. So, how can we kind of explain this? We can do that using our energy conservation understanding. So let's think about this. What happens? You walk in suddenly to a warm building. So what do you have? You have cold glasses interacting suddenly with warm air. So we know how heat will flow. The heat will flow from the warm air to the cold glasses. So the glasses will start warming up. So the thermal energy of the glasses will go up. They're not going through a phase transition, they're just getting warmer. Now, what does that mean? It means that the energy of the environment, or that warmer air that's heating the glasses, has to go down. Now, the air itself is, a gas composed of different molecules. One of them is water. So what happens is, as its energy goes down, what happens, it's actually some of those steam molecules, which are in a form of gas, go through a phase transition where they condense. That's why we often call this condensation. They condense and turn into water droplets. What is fog? That's actually the presence, when you take your glasses off to clean, they feel wet. That's exactly why. It's literally water droplets that are condensing from the air onto your glasses. So thermal energy goes up, bond energy of the steam or water vapor goes down, which creates liquid particles on the glasses. It's the same idea of why it feels like, again, on a hot day, your cold drink is leaking water. The water is not leaking, it's not escaping. That water is not coming from the glass itself, it's coming from the air. It's the same idea. Thermal energy of the glass is going up as it's interacting with the hot air outside, which means that the environment has to be losing energy. It's losing that energy in the form of a phase transition of steam going into condensing into water. So this water droplets is condensation of the air around. So kind of same exact concept that makes your glasses fog up as makes your glass feel like it's leaking when you're drinking it outside on a hot day. Another kind of common experience, especially now during the pandemic, you're probably using hand sanitizer quite often, and you might have noticed that often when you use it, your hands feel kind of cold. If you haven't, pay attention next time you use hand sanitizer, your hands suddenly feel really cold after you've used it. So what's going on there? Well, hand sanitizer, this often has rubbing alcohol and things like that vaporizes very easily, because you rub them together and there's no longer liquid there, it all vaporized. So what is the process of vaporization? It's the bond energy of the hand sanitizer going up. It's interacting with if it's going up, that energy has to have come from somewhere. Well, it's interacting directly with your hands. So that energy is being taken from your hands in a form of thermal energy. So the temperature of your hands goes down, bond energy of the hand sanitizer goes up. That's why your hands feel cold as this hand sanitizer vaporizes. All right, so I think that's all for today. Next recording, we will continue to talk about, we will wrap up this thermal energy material from now, and we will move on to talking about mechanical energies. So energy transfer due to work versus heat will be the main focus. Thank you for listening. Bye.